Okay, thank you very much. Thank you for introducing me. So I will indeed set the scene. I think I will reset the scene. It will act, I think, as a refresher of what we've heard this morning. So I have prepared a series of slides, so bear with me. Fasten your seatbelt because it will be quite fast, I guess. I first would like to bring you into what I call the renewable time. So if you go back in time, well, typically in the time of Anneg, but even back in 1800, we were only using 7 metals. We were in those times essentially using renewable energies only, so charcoal, windmills, water mills, and we basically used like 3 to 4 manpower per day. Today we know 91 metals. We've invented all the metals. We use them in any possible application. Every metal has a specific use. We are relying on a lot of non-renewable energies, and roughly we're using 100 times more energy for our daily comfort, for transportation, for heating, for all these things. So this is a reality. So metals are everywhere. They all have different uses. I will focus a bit more on nickel because it's one of the main driver here of the discussion today. So nickel is everywhere, including in your pocket. So this, of course, here, for those who understand, I left the title in French because it does work. It refers to Magritte, a bit of surrealism. It's indeed not, it's money, but it's not silver. Just to tell you, if you're not aware, that even the euros are made of complex alloys, and not 2 of these alloys are the same. So keep that in mind, because I'll come back to this example of money. No, money is, of course, a very limited use of nickel. Most of nickel is used in stainless steel. And these 2 hooks, they look exactly the same, but in fact they're not. One is stainless steel 304, the other one 316. It doesn't seem important, but keep that in mind. When I speak about recycling, you will understand it's quite a challenge to make the difference between the 2 and to identify the one that contains molybdenum and the one that doesn't contain molybdenum. So, as we said this morning, we now have a lot of flows of metals. We need to monitor all the uses and all the statistics. I must say for decades, nothing was going on. I'm happy to see that now Europe has this raw materials information system. So if you're interested, you can have a look at the dashboard. This is the dashboard of nickel, and you see how uses are distributed. So please keep in mind that essentially today the driver is stainless steel. 80% of the market of nickel is still stainless steel. Batteries 8%. It's increasing, obviously, but it is multiple uses and multiple possibilities for a given metal. Okay, we speak a lot about green growth. Okay, we can discuss possible degrowth and maybe change our behavior, but here when we come to the Green Deal, the energy transition, we will be faced with the need for much more metals. Take any metal and you will have this kind of curve. If you start 1900, everything is exponential. Copper started with electricity in 1900. Nickel waited until after World War II to become really used. So you see starting 1945. And a lot of metals like indium started only in the 80s with electronics, but all are increasingly used, and this will probably not be stopped. I see no way to stop this curve because we said it this morning, it's population growth, it's access to higher living standards, but it's also technologies that rely more and more on metals. So when I see this, I must say I'm asking myself a lot of questions. This is representing the GDP, European GDP, which is growing, and we see the raw materials consumption, which is going down. So indeed, we tend to say that we manage to keep our growth by using less resources. The truth is that it's apparent raw materials consumption, so the statistics, as far as I know, I'm not a specialist, I had to try to understand it a bit better. Those statistics are not at all reflecting all the metals that we're importing in the form of finished goods, such as cars, computers, batteries, that all come from Asia, mostly come from Asia today. So I really doubt that our raw materials consumption is going down, that we're really heading towards dematerialization. So this is eventually a topic to be discussed. Okay, we heard this morning that some examples of supposed dematerialization exist, like the thickness of polysilicon solar panels. Yes, but in 1990, no one was really putting solar panels, and as you see today, the technology is stabilized at 100-micron slices of polysilicon. So yes, okay, we are using a bit less silicon than before, but don't expect that we'll go to a few microns of silicon in future panels. So solar panels are resource intensive. Other examples, no comment. If you compare the Mini of 1960 with the Mini of today, especially the electric Mini 2021, it is about 2.5 times the weight of the previous car. Okay, For the same mobility, or, well, mobility, which I'm not counting traffic jams. For, let's say, for the same mobility, of course, we've improved security, etc. So let's discuss it, of course, with more details, but I think we have to really look at the use that we're making of our resources. Okay, this you saw this morning. So obviously, the fact that if we want to go towards electric mobility, the fact that if we want to install solar panels, batteries, etc., we will need much more resources. These graphics do not take into account iron and aluminium. If not, we would be completely out of the screen, even out of the room. So, okay, everyone already discussed circular economy. I would like to introduce circular economy very quickly. Sorry for rushing. Yes, okay, we want to go circular. We have to go circular. How come that we forgot about circularity? I mean, it's obvious. There are cycles everywhere in nature. So if you want to mimic nature, you have to think in terms of cycles. We forgot for a while. We are what I call the big generation. You still have old pens. These are disposable pens, I'm quite sure. So we are the big generation. This is finished, definitely, and we will try now to have a circular understanding of our metals. But when you speak about circular economy, please keep in mind, it is not at all a circle. It is not a circle today. It will still take several generations before we manage to have a full circle. So this representation of the circular economy, which is the one of European Parliament, is correct in the sense that there is still an input and there is always waste. So I see circular economy as essentially 4 challenges. There could be more, but the ones that I would like to address are feed the loop, design the loop, slow down the loop, and then close the loop. Let's quickly review those different challenges. So feed the loop, well, yes, I'm a proud extractivist. I'm sorry, but I hate, of course, this term. I'm a resource engineer. I'm looking for resources, and we will need resources. We will need to feed the loop. A lot of metals were not used before, so they're simply not available for recycling. But even nickel that we use since 1940, if you take all the nickel which is available for recycling, if you manage to collect it back, which is impossible, if you perfectly recycle it, you will have at best a production of 1980, which is representing 30% of today's use. So very simply, sorry, it's extremely simplistic, but telling you that without mining, you will never satisfy current needs. So we need more nickel quickly, because we didn't hear a lot about this morning. So I'd like to give some input, because we'll be discussing deep sea resources. Nickel is a very abundant element. So I can tell you with 5% of nickel, the pity is that it's 3,000 kilometers down here in the Earth's core. Then we have roughly 0.2% nickel in the mantle. That's a bit low. So what we're targeting today is everywhere where this magma, this ultramafic magma, comes to the surface. And the good news is that when this magma comes to the surface, typically in the oceanic floor, if that oceanic floor is exposed to tropical alteration, then we have what we call lateritization, and we have these fantastic rocks containing not just 0.2% nickel, but up to 1.52% nickel. So this is what we are mining today. As Gavin Mudd said before, this is one of the main sources of nickel. In tropical environments, we can discuss biodiversity, environmental impact. That's one possible source. If you're not happy with that one, we have another one, which is nickel sulfides, basically where this magma crosses sulfide sources. In some typical environments, we have massive sulfides that form. They are being extracted, like here in Australia. The picture you see is Liége Lake. So don't worry, it's not snow in Australia, it's salt, okay? You could have the same picture coming from Norilsk in Siberia, so quite extreme cases. The problem here, we have nickel in the form of sulfate. So I forgot to mention before, in laterites, we have nickel in silicates. They're quite hard to dissolve, and it's quite hard to extract the nickel. Here, sulfides are a bit easier to work, so less energy. I guess Jo will comment on that. But you're left with sulfur. You have to deal with sulfur and with the environmental impact of sulfur. And then we have a third source that has been untouched until now, because we didn't have the technology to go that deep. If not, they would have been taken since ages. I mean, they are the easiest to collect if you did not have this challenge of engineering of going down 4.5 kilometers under water column. These are the famous polymetallic nodule. They also have like a similar grade. The good thing, you don't have gangue here. And you have a material which is in the form of oxyhydroxides, which is also much easier to work. So I don't want to take a position. I'm just telling you we have 3 sources. And if you want to put things in a balance between the sulfides, the laterites, and the polymetallic nodules in terms of any kind of impact, and probably we'll have a discussion afterwards, it is not an easy answer. I see time flying, so I'd like to switch to circular economy back again. My main message as a geologist is that we still have plenty of resources, so we should not worry too much about that, but we should worry enormously about what we're doing with those resources. What are we making, guys? Look at this picture, it tells it all. We had very simple light bulbs, a little bit of tungsten, a little bit of glass, a little bit of steel, so minimum resources. They were using quite a lot of energy, I agree, but they were also extremely easy to recycle. The ones of today, at the right-hand side, the diodes, I don't need to tell you all the details. 5 minutes more. I'll rush a bit less. Okay, thank you. Then I'll slow down a bit. You'll see it's important to slow down. I know I have too many slides, but okay, let me tell you this. So here we will need as many resources as in any smartphone for these light bulbs, okay? And you can also imagine, so we're mobilizing dozens of resources and we have big problems in terms of recycling at the end. Basically, they're not recyclable, but we can discuss it too. So there's something there that needs to be done and we need to have a complete vision. We should not just look at the use phase. If not, there is no discussion. Diodes are much better than the classical light bulbs. But if you take the full picture from cradle to cradle, then maybe there is a real debate between what is the best technology. And I'm not far from thinking that it could be to go back to the good old tungsten lamp. What I just illustrated with this tungsten bulb is valid for almost anything. As Peter just said, the good old lead-acid battery is a perfect technology which is perfectly recycled. So if I had to give a first prize to a technology, it would be that good old lead battery. The problem, of course, is we are not going to have electric cars with those very heavy batteries, so we have to go to other batteries. If I could give another prize, I would give it to this small coffee machine, this Italian Bialetti. Pure aluminium, no mechanics, no electricity, and you have a superb coffee. No, I'm not joking. And the third one are these copper tubes. Thank you. See the Italian. And the third prize would go to these copper tubes that we used to produce in Liége, and that have disappeared. We closed down, Chinese took over the company, and now we're making these Alpex tubes. If you want to have tubes, you have these Alpex, which are composite material. Okay, they're easy. In terms of functionality, they're perfect. But in terms of mix of material, it's a nightmare. We're not going to recycle brass, aluminium, and polyethylene that is in those tubes. So we went the wrong way. The same with the coffee machine, obviously, despite what Nespresso says. I think I can say it here, right? It will not go into the media. So despite what Nespresso says, it's a very poor idea to have aluminium thrown away for each cup of coffee. And for batteries, we have to go, of course, to these new lithium-ion batteries, all kinds, but they are absolutely complex in terms of internal structure. So what is complex to manufacture is awfully complex to de-manufacture. So, okay, I said it already, so let's stop with single use, definitely. Let's finish with the big generation. That's one of the main messages. Let's slow down the loop. Let's keep things for long. When I think about things that we should keep for long, I think about my own city, this railway station. You can love it or hate it, but the fact is that the previous one only lasted 50 years. 50 years for a railway station. So I always wonder, looking at this one, when will we throw it down? And I hope it will last at least 1,000 years. So it gives you, or maybe only 500, but it gives you some perspective. Everything we build should be built for ages, for centuries. Smartphones could also live 50 years if we wanted. So we definitely have to work on that. We have to slow down the loop because we cannot keep consuming like we do. Now the final step, so after, okay, slowing down the loops means also right to repair, being able to repair, reuse, etc. Now coming to the recycling phase, so to closing the loop, everyone is extremely positive about recycling. I guess we'll discuss it in the debate. Indeed, but it's not an easy job, and it does require a lot of innovation. It does require to mobilize a lot of technologies, because when we speak about recycling, first, it's all about collecting back. So if tomorrow you install a lot of solar panels in the middle of Africa and batteries, think about how you're going to collect them back to a plant capable of recycling. Second, it's about fragmentation, dismantling, sorting. Okay, you're all sorting at home in a few bins, but here we have to sort in hundreds of different categories, and when I say 100, it's an underestimation. And then we have to find the best recipe in terms of pyrometallurgy, in terms of hydrometallurgy. There are pros and cons depending on technology you use. All these to come back with new materials that we can reuse. And reusing, sorry again here, a lot of recycling. We're recovering metals, and then we sell them to the Chinese. So is that what we want? No. Well, if we want to reuse those materials, we need to re-industrialize. We need to redevelop the whole value chain and be able to reuse those metals in our own region and make sure that the circular economy closes the loop, at least at the pan-European level. I would even say at a regional level, something like 500,000 kilometers diameter. So I'll bring you back to, don't know what, okay. So I'd like to bring you back to my initial examples of money and those hooks, just to challenge you to say, how are you going to sort them? How are you going to identify the different alloys that are inside these pieces? Of course, the money, they were made with different diameters, so it's quite easy to separate them by size. And money, no one throws money in the dustbin, so it's quite easy to collect it back. That's not I'm not too worried about money. But already these 1 and 2 euros, remember, they're polymetallic. So you have to invent a technique to separate the grayish alloy from the yellowish alloy in your 1 and 2 euros coins. Okay, it's not really a challenge for engineers. The other one is much more a challenge. How do you identify the difference between these stainless steel? They look exactly the same. So what we're developing now in different places, especially in my lab, are these robots, which are doing what we call smart sorting. So they have sensors and systems that allow them to see the composition. So there's a lot of innovation needed there to be able to split those different alloys and hopefully then remelt and make immediately new pieces of stainless steel. So I'll finish with this. I'll finish you by presenting the end of the world. The end of the world is this. I haven't found a better illustration until now, so I tend to think in terms of a big plasticine Play-Doh game. So initially we have resources, we have these different colors, we start making a lot of objects and products. If we're extremely careful, we'll be able to dismantle them, to separate, and next generation will be able to play with the same plasticine. If you're not careful, if we mix everything up, what we're doing today in electronics in particular, well, it will all end up in this brownish, dirty color that you all know, what we call entropy, total disorder. And as you see, I'm writing entropy because it will be human responsibility if we arrive at that point. So I hope it will not be the end, but thank you.